SEG BHU Student Chapter welcomes you all to this online lecture cum interaction session with Professor Mrinal K. Sir, Jackson Chair in Applied Seismology, Institute for Geophysics, University of Texas. I thank all of you for joining us today. I owe a short introduction to all. I am Pankhuri Thakur, student of MSc Tech Geophysics at Banaras Hindu University and External Affairs Head of this year's SEG Student Chapter team. I will be your host for today's session. This evening, we have a very wonderful guest with us, Professor Mrinal K. Sir. Before we begin, I would like to apprise about Sir to you all. Sir is a specialist in seismic wave propagation, including anisotropy, inversion, and uncertainty quantification. He has extended seismic plane wave analysis methods to anisotropic media and developed novel methods for characterizing unconventional reservoirs. He has carried out rigorous error analysis of finite element and finite difference methods and developed several efficient finite difference operators for modeling and imaging. There is a lot more to him that we will find out through his lecture. It is a great honor for all of us to have Sir with us today to guide us on full waveform inversion. I would like to inform all the participants that at the end of this session, we will have a short interaction wherein all the doubts that you have raised through this session can be put in the chat box and will be discussed and clarified by Sir. We will also provide a feedback form and I request all of you to fill it at the end. Also, for your prior information, the whole session is being recorded so that we can upload it on our YouTube channel. So now, I think we are good to proceed, and thus I again welcome Sir to start the session. Over to you, Sir, please.
Okay, let me share my screen. Okay, so can you see my screen and you able to hear me okay?
Yes, sir, it is.
Okay, so thank you for the introduction and thanks for the invitation. It's indeed a pleasure for me to be here. It's morning time. And I'm going to go over some of the fundamental concepts of full waveform inversion, which is one of the most popular algorithms for seismic data analysis these days. This is the general outline or general content of my talk. I will go over the introduction and motivation behind FWI, and then the most important aspect of FWI is forward modeling. So I'll try to talk about it very briefly, giving you an overview of how forward modeling is carried out, and then talk about optimization. These two steps are essential or crucial for FWI. And therefore, I'd really like you to pay attention to these. And these basically are part of the theory, but then there is another part, it's called adjoint calculation, which I will go over. And then I would like to outline some of the problems that we encounter when you try to use FWI. And then finally, I'll show you a field data example. All right, so it all starts with data. Seismic data. So here is a model. This is a synthetic model of a salt model. This is SEG EAGE salt model. So here you can see salt body. This is very high velocity layer. So velocity, Q-wave velocity about 5 kilometers per second, as opposed to sediment velocities that can be anywhere between 2 and 3 kilometers per second. Now, if in a model like this, if you fire a shot at this location, these waves will propagate. They get reflected, transmitted, and refracted, and then they basically arrive at different receivers. So in this experiment, I put receivers everywhere along this line. Now, if you look at the shot gather, what you see here is a very complex structure here. This is your time, and that's your offset, or location of the receiver. So first of all, what you notice is a first arrival, which is the direct wave, and then there is some some reflections, and there are reflections from the salt body and so on. This is not symmetric. This is not very regular, layer cake structure because of the presence of salt body, and that is the reason why your short record looks actually fairly complicated. But this is something that we don't know. This is an unknown. What we have is a whole bunch of short records. So the problem here is, how do we go from this to this? That is the fundamental problem. And that is our inverse problem. However, if you assume certain subsurface velocity structure, can you generate some data using some numerical algorithm? And that would be our forward problem. Now, in order for you to understand subsurface seismic structure, the most important parameter that you need to be able to estimate is seismic wave velocity. And now there are many ways that we seismic wave velocities that are based on different levels of approximation, and therefore they have different kinds of accuracy. The first thing that you learn in your seismic processing class is what is known as normal move out, and this assumes locally 1D flat structure, and what you get out of this is some kind of effective velocity. It's called RMS, root mean square velocity. We can look at the amplitude also as a function of angle or offset, and that can give us a slightly better estimates of velocity. But still it's under 1D or flat lying. When I say 1D, the layers are flat. Okay. On the other hand, when you go to the last two, you have seismic tomography and full waveform inversion. These two methods basically work in laterally heterogeneous medium. What it means is that the velocities can vary in all directions. So that is really the kind of problem that we always deal with. We try to approximate a 3D model by locally 1D models, which gives us something that we can work with, but it's really not the most accurate way of solving for, or most accurate way of finding velocities. Therefore, we need tomography and full waveform inversion. So, if you look at this particular picture, this is a function. This is the velocity plot as a function of wavelength, or the variation in the velocities in the subsurface. And it turns out that we have, if we use just the tomography velocities, you can get low frequencies up to this particular wave number. If you use AVA, you can get this band, but this band is missing. And this is your low frequency data that's actually missing in the seismograms. So the goal here is to use something called full waveform inversion that makes use of the complete seismogram, whatever information is contained in the seismic trace, which I'll talk about in a second. So this is a very nice picture. Tomography gives you low frequencies, low wave numbers. Migration velocities migration or reflectivity that can give you velocities in the seismic frequency range, amplitude that is sensitive to amplitude. On the other hand, FWI, the hope is that it will fill up the gaps. In that case, we are hoping to get a complete description of the seismic wave velocity, because tomography and migration velocity, these are contained in FWI. So, okay, so since some of you are probably new to seismology, let's start with the short record. This is the field data, and what you see here are some arrivals that are marked like red and yellow. So the red is direct P wave velocity. Yellow, these are some reflections. You can see a lot of these reflections. These are reflection hyperbolae. And we have some arrival here. These are surface waves and converted shear. And then you have all of these critical reflections, post-critical reflections, or turning rays. And these are generally, in standard seismic processing, what you would do is you would just mute this part and only focus on the reflection. And by doing that, you are actually throwing away some very, very important information. And I'll tell you why. Here, let's say that you have these velocity models. Now, you can build a complex velocity model using these as basis. So for example, you have this particular example, you have a layer over a half space. And this second one, this is basically continuously changing velocity. This is a gradient velocity model. Now this is a combination of a homogeneous layer and a layer with velocity gradient. And this fourth one is basically a layer with a homogeneous velocity, and then the second layer has a velocity gradient, but then there is a discontinuity in the velocity. In other words, the second layer velocity starts at a value that is higher than the first layer velocity. And you can combine these to come up with more complex velocity models. Okay? So you need to know what happens when you have different velocities here. Okay, so we were in this, and what I was trying to say is that if you mute this, you are actually throwing away a lot of very important information. So let's look at what happens for simply two homogeneous layers separated by a velocity discontinuity. So you have a source, and these are the receivers. So you can have a direct wave, and then you can have reflections from the discontinuity. So what you see here is this the direct wave, this is the reflection. Now there is another arrival here. Can somebody tell me what that is? This particular phase, does anybody know what that is? Those are called head waves or refracted waves. So when the ray reaches critical angle, there is a ray that goes along the interface and then comes back up. Okay, and this angle is the critical angle here, and that propagates with the velocity of the lower interface. Here we assume that V1 is greater than V0. If V1 is less than V0, you will not see a head wave. Okay. Now the other thing that can happen is when the lower layer has a velocity gradient. When you have a velocity gradient, then the rays actually turn like this. Okay. And these are called diving waves. And these diving waves can be multiply reflected like this. So if you plot those travel times, you see this is the direct wave, this is the reflected wave, and then you have diving waves, and then diving waves with multiple reflections can actually may appear like head waves. Okay, so this is something that you have to be aware of, that in general, for head waves to occur, you need a perfect discontinuity that may not actually happen in real world. In reality, what may happen is that the velocity, the lower layer is continuously changing, but then these turning rays, multiply reflected turning rays, may appear like head waves, but then they have higher amplitude. Okay, so these arrivals help us to find velocities of different layers. Alright, so what is seismic tomography? So in seismic tomography, what is done is, let's say that these are some short records. Can you see this? So these are different short records. So what is being done here is we have Okay, so you can see in these short gathers, there are some red dots here. So what has been done is someone picked these first arrivals and read the time of arrival of these different arrivals. And these these travel time, peak travel times were then used to estimate a velocity structure. This is the velocity that was derived by locally 1D, say NMO, and then this is what one obtains by tomography. So this is the result of tomography, and that shows that there is a Bayesian kind of structure here. Now, if we take the same data and run full waveform inversion, so you don't need to pick any of these arrivals, but you need just put in that complete gathers, but use this velocity model that was derived by tomography as the starting solution. And now you can see the details of the velocity structure that you can see. You can see how it has picked up a lot of these reflections, a lot of these layers which caused reflections. And this is the kind of velocity model you want for carrying out your interpretation work. Because this just tells you, this gives you gross structure, but this one actually gives you some of the details. Okay? So I wanted to start with an example here. This is a cross well experiment where you have one well on the left and one well on the right, and these are different wells. So there are 3 wells here, and if you look at the well log derived velocities and simply plot those at their locations and do a interpretation, you can say that these are perhaps my faults by correlating the velocities, but you don't know what is going on in between. And here is what is called a VSP gather. Okay. Now there are 2 ways to actually get the velocities. This is obtained by using tomography, and this is the one that has been obtained by full waveform inversion. Okay. So what you see is that with tomography, you can get some kind of a smooth velocity structure. But with FWI, now you can see some of the details. This part gives you some kind of a hint about the fault location, but this actually has brought out the faults much better. The same thing has happened here. So you're able to understand the subsurface velocity variations much better using FWI than with tomography. Okay. So this is a table that outlines different methods, different kinds of data, and how they are used in different inversion. For AVA, or amplitude variation with angle, we use amplitude only. For tomography, we pick travel times. For FWI, we use the short gathers. And they use different kind of forward modeling operators, which I'll talk about in a second. Okay, so if you look at how seismic processing technology has developed over the years, in the early stages, we were only using travel time information for time imaging. Then we moved into something called depth imaging, where we were able to, where our focus was to actually get information on the subsurface variation in real world that is in depth. Because to go from time to depth, you need to have the velocities. Then came something called reverse time migration, which is a more complete description, which uses more complete wave equation or more complete wave propagation models, and it gives you much better depth images. And then came least squares migration, which is even which gives even better image. Okay. Now we mostly use FWI, even though this should have been the chronology of development, but the theory of FWI was proposed before least squares migration, and we put it in the back burner because this is a computationally very intensive process, and until the computers became faster, we never bothered about about implementing FWI. But there's one thing that is common. That is, it needs velocity model. And to do that, we have to make use of wave equation and simulation of seismic wave propagation in your computer. So I'll give you a very brief on the theory, a very brief outline. There are two fundamental equations in seismology. One is your equation of motion. This is your density, this is your displacement, and that's your stress tensor, and this is a body force. And this is your stress-strain relationship. So this is your Newton's law of motion, second law of motion, and this is Hooke's law. And these are the two equations that you actually learned in your very basic physics, maybe first year physics. But just that they are written in a way that is a bit more complicated, that basically confuses you. But you already have the basic knowledge of the equations that are used in seismology. Newton's law of motion and Hooke's law. So this is balance of forces, and this is basically the relationship between stress and strain. So from these two equations, you can derive your wave equation. And you can get a very general wave equation for anisotropic media, or you can reduce it to elastic medium. But for today, we're going to focus on acoustic medium. In acoustic medium, we have a scalar wave field, typically the pressure, and this is time. This is your velocity, and this is your force term. So this P is a function of x in t, where x is the coordinate of a particular point, and t is a function of time. So you can solve this wave equation to compute pressure variation as a function of time and space. And for that we use finite differences. It's quite simple. All you do is you do Taylor series expansion, and you write down a discrete version of the derivative operator for p, x, and z, and you can rearrange the term, and you get an equation that tells you that if you know your pressure value at some t and t minus delta t, if you know the current pressure and the past pressure, then you can predict what the pressure is going to be in a future time. So this is basically a time marching algorithm. So you initiate with the pulse, which is the source term, and then you can propagate. So this is an equation that you can code very easily, and you can actually see what is going on in the subsurface. So the way calculations go is we define our zone of interest marked by blue, and then we have some padded zones, and you can put the source anywhere, and the receivers can be anywhere because it computes wave field everywhere. And then you can look at how the wave field is changing. But this is your velocity model. Now this is something that you have to input. Okay. You can solve the same thing in frequency domain, but I'll skip that. So what is done in full wave imaging, a reverse time migration, is you forward propagate the source wave field and backward propagate the data. You can do cross correlate, and you can obtain an image. Okay. So, but this is migration. Migration does not give you complete description of the velocity field. So then we went to something called least squares RTM. So here input data is run through reverse time migration, and that gives us reflectivity or reflection coefficients. Then we use Born approximation to generate synthetic data, and then we iterate until we are able to fit the data. But this is not something that I want to talk about. We're going to talk about FWI. So what is done in FWI? In FWI, what we do is, let's say that this is the model that we're after. We don't know what the model looks like. All we have is a bunch of short gathers. Okay. So then what we do is we assume some model, some initial model. And that can be flat layers, it could be homogeneous or whatever. And then we use our finite difference operator to calculate our synthetic data. What you see is that when this model is very different from what actually what the subsurface actually looks like, then the predicted data is not going to look like the observed data. So we take the difference, and then what we do is take the help of this residual to come up with a correction to this model. And we add that correction and we go through this loop until our data here, predicted data, matches our observed data. Is this clear? Because this is the most important part that you need to understand. This is an iterative process. You start with the observed data and some kind of starting model, starting velocity model. This could be derived from tomography or any other independent information. And then here you use the forward modeling operator and you calculate data and repeat this. Okay. So what you see here is that the total number of shots really decides how many forward modeling you have to do in each iteration. So this can be very, very time consuming. So here is the optimization flowchart. This is your model parameter that you're inputting. This is your forward modeling. This is predicting to the data. And this is measuring the difference between observed data and synthetic data. And then it's basically minimizing this function. And that is called optimization. And the way it's done is what is known as gradient descent algorithm. So you start with a point. Here, let's say that this is your objective function, or the function that you want to minimize. So you start with a guess and you compute its gradient. Now the gradient is the direction in which the function is increasing. So you go in the negative of the gradient direction and you decide how far you want to go. So you have a new starting point. You evaluate gradient again and go in the opposite direction, then you have a next starting point, and so on. And after some time, you will see that the gradient becomes almost zero, so you don't have to iterate anymore. Okay? So this is the heart of the algorithm. And the only thing that's different here is that you have to calculate the forward model or the synthetic data, and you have to be able to calculate your gradient. Okay? Now for gradient calculation, we use something called adjoint state method, which I will not really go into details of. You can find those in my notes here. If you have any question, you can ask me later. Okay? And this is how we actually calculated the theory part I've shown you. So this is your source wave field. Okay? So we generate your synthetic data, we propagate our source wave field, and then you take the residual, the data, the difference between observed data and synthetic data, and propagate that backward in time. And then you cross correlate. And this gives us information on the gradient. Okay? So this can be done using equivalent of one forward modeling calculation. Now this also I'll skip. What are the problems with FWI? So first of all, I think based on the discussion, based on what I said so far, you should be pretty clear as to what is done in full waveform inversion. You start with data, initial model, then you calculate your synthetics, you calculate your gradient, and then you find the best model, right? Iteratively. So the biggest challenge is computational cost, and there's something called cycle skipping. Okay. All right. So if we look at what is it that we are calculating, this is our observed data, which is a function of source, receiver, and time, and this is our synthetic data. This G is a forward modeling operator. And this is something that we need to evaluate repeatedly along with the gradient. So, and this is summing over all sources and all times. The total cost will be number of iterations times the cost per iteration. So the cost per iteration would be like number of times you're doing the adjoint calculation or the gradient calculation, number of times you're doing the forward calculation, and also we need a few of these trial forward modeling operators. So one thing that came out handy is rather than putting in the sources separately, what if we add those up and just run it once, generating a super gather. So what happens with the super gathers is that you see some crosstalks from different shots because the experiment was actually done separately. So first of all, you fired a shot and then you waited for some time, then you fired the next shot. If you fired separate shots simultaneously, the signal from each shot will be arriving at the receiver at different times, but they will mix it up. And when you try to image it, you will see this kind of crosstalk. So how do I actually separate those out? And the way to separate this out is something called phase encoding. And what is done here is you just sum the shots with some random phase shift. Okay, and this is an idea that came from electrical engineering signal processing. And after doing this, you are able to separate out the different shots. The same idea can be applied to migration. So here is an example of my migration. This one is the true model, and this is migration using phase encoding. And this is the difference between the two. So when you use all the shots as opposed to just the super gather, you can see that you can get as good a result as using all the shots. Of course, there'll be some differences here. So that helped quite a bit, and a lot of the companies are actually using phase encoding in their FWI. So the next thing that we wanted to talk about is cycle skipping. Now, cycle skipping is what happens when, let's say that these are the red. This is your target seismic trace, and you have your synthetic seismic trace would look like this. So it turns out that as you shift your synthetics along the real data, and you look at how your error is changing, you can see that it goes through something. This is one minimum, then it goes through here, then it finds another minimum, then it finds another minimum. So these are local minima, and this is your global minima. This is what you want, but the gradient descent method actually gets stuck in this. So then how do we get around this? There are many different ways of doing this. One of the most common approaches is to start with a smooth model and lower frequency, and then increase it. So this is an example of a local minimum problem. This is your exact model, and this is a very good initial model. So then your final result looks close to the true model. However, if you start with this initial model, you can see that it gets stuck in the local minimum, and it gives you a model that is very, very different from the true model. Okay. Now this is something that everybody has to deal with who are trying to use FWI, and if you get a job in the industry and you are asked to carry out FWI, this is a problem that you have to deal with. So there are different ways of doing this. One is multi-scale, where you actually start with low frequency and add higher and higher frequency. Then there's some tomography, velocity, full waveform inversion, Laplace Fourier domain. There's something called global optimization method and mini batch. And I'm not going to go over all of these methods because of lack of time. Just wanted to show you how the model changes as a function of frequency. So if you start with 0 to 3 Hertz data, you get a model that looks like this. Then this becomes your starting model. You bring in data from 3 to 6 Hertz now and run inversion, so you can see that some of the details have been picked up. And then after that, if you go to 6 to 9 Hertz with this as the starting model, even more details are coming in. So after you have gone through a few steps of frequency staging, around 15 to 18 Hertz, you get a model that looks very close to the true model. Okay, so this is one approach that you can take for mitigating cycle skipping problem, and this is one of the most common approaches for doing this. And this is your true model, this is your starting model, and this is your inverted model. Okay. I will skip the hybrid method, and I will talk about a real data example. This is an example that you'll find in this particular publication. It was led by Carlos Calderon, who is the vice president of the company, is a former student of mine, and so I will go over the results from there. So here the goal was to derive a velocity model from a narrow azimuth survey in Mexican side of the Gulf of Mexico. And here they made use of diving rays and reflections. And this area is characterized by folding, gas-bearing sand channels, and faulting. Whenever you start a project in the industry, there'll always be some geologic objective as to why you're doing this, and you'll have some ancillary information from that area. Now this area, they knew that this is characterized by folding, this has some gas-bearing sand channels, and there are some faults. The reflection tomography, which I talked about earlier, that was able to capture the overall trend of the reflectors, but the details were missing, and that's where we really need FWI. So this is the study area from Gulf of Mexico, and this area of interest due to large gas accumulation in structural plays. And this acquisition maximum offset was 8 kilometers, water bottom was approximately 2 kilometers, and there was some standard processing done to the data like deghosting and multiple removal. And this was a fairly decent sized project, it's about 750 square kilometers. Alright, so you can see the model progression and final RTM image. This is the ray tomography. This is diving ray, but we did not use diving rays. This is just the ray tomography. This is diving ray, so you can start to see some more details here. And this is diving ray plus reflection tomography. So this is your final model. And using this, if you apply RTM, this is what your RTM looks like. And for comparison, they actually had a well drilled in here. So you can see that the well was not matching very good in diving ray and ray tomography. In fact, they were giving you a smoother version of well log. But when you come to the FWI model, you can start to match the well better. Okay, and you can actually see what this looks like when we put it on top of the RTM image. You can see that the structure right there, it picked the velocities quite well. And these are what you call common channel gatherers. So this is a comparison of the data that you predicted, which is in green, and the data and the actual data, which is in black. So you can see that more or less it's actually matching quite well. Okay, it shows you different parts of the time window. Now this is the kind of plots that you will be looking at when you are carrying out an interpretation task. So these are depth slices. So this top one, this is your ray tomography. This is your ray tomography, and then this is your final FWI model. This is at one depth, 2860. And then so now this is your final FWI model at this depth, at 2860. And if you look at the migrated image slice, this is really beautiful. You can actually see the channels and all the structures. This looks like a real subsurface geology. Now this is another depth slice from another depth. This is at 4620 meters. This is your ray tomography, and this is your FWI model. It's a big difference. You can see all of these details, but when this FWI model is used for RTM, and you look at the slice, you can see all the details. It's really, really mind-boggling. And then they also compared some of this, so I already showed you that. Yeah, this is important. Again, you can actually see how the channels are imaged in this depth slice. And these are very, very important for exploration targets. So this is a comparison of the velocities only. This is the tomographic velocity, and this is your FWI. You can see all the details here. Not every little details, but the most important parts of the model have been picked up. Still, you will not get the same resolution as the well, but you can see it's in between, and it fills in a lot of the details that are missing in the tomographic model. Okay, so if we were to prepare a cheat sheet in terms of what is it that you need to know when you are running, or you want to run an FWI, or you think that you are an FWI expert. So why FWI? Okay, this is something that you have to know. Then you need to know what do you need FWI for? Okay, and I hope I have answered these questions for you. And how does FWI work? What can you learn from FWI results? What are the problem areas? Now, these 5 questions I have already answered in my talk. So if I were to give you a quiz, you should be able to answer these easily. Of course, I'm not going to give you a quiz today. And one thing that I wanted to mention is that FWI method has been applied not only in seismic exploration, but also with earthquakes data for whole Earth imaging. It has been applied to GPR, medical imaging, and non-destructive testing, where you want to find some damage in a particular structure. So if you look at the history of the development of different methods, it's actually kept in pace with the complete power increase. So in the right hand side, I'm plotting the year. It's pretty old, it's 2011. So what you see is that over the years we started with pre-stack depth migration. Then we started using clusters of computers for doing that. Then we did Kirchhoff full volume. Then we did wave equation. We did anisotropy. We did beam migration, and then we did RTM, TTI RTM, and now we're using GPU clusters, FWI. And this is possible only because the computational power has increased. So what is different between these methods? It's basically, as we progressed, we included more complete physics. Okay, so we started with very simplistic assumptions. It's not that we didn't know what is the correct physics to use, just that we could not afford to make all those calculations. Okay, so the road ahead, we will see in future elastic FWI, which can be used for quantitative seismic interpretation. We will see anisotropic FWI, and there's quite a bit of work going on in uncertainty quantification. And we will also come up with some better method for cycle skipping. And the modern trend is also to make use of some of the deep learning method, machine learning methods to take advantage of the developments in that field to see if you can make your algorithm faster. So that is all I had, and I would like to stop here and be happy to have some discussions.
Thank you so much, sir. We are very grateful for delivering such an informative and engrossing session. And with your permission, I hope we can start the interaction for any doubts the participants might have. So I request all the participants to put forth their queries in the chat box, or if you want to ask them directly, you can raise your hand or just unmute yourself. And I understand it has been a very interesting lecture, but please be decent and please go ahead. So we'll wait just for a few minutes for them to put their queries.
Sure. Well, looks like there's no questions, so then let them try to answer those questions I gave in the cheat sheet.
Yes, sir. You explained it quite well, sir. I don't think anyone might have any doubts.
Okay, so who wants to volunteer answering those questions?
Anyone who wants to answer? Questions from sir's cheat sheet or any others?
Why do you want to do FWI?
Anyone?
It's like for getting more detailed images, because in 3D tomography we are not we are getting like layering we can get, but more detailed image we are using FWI. So
Good, very good. All right. So, what do you need for FWI?
I think with advancement in the computational framework, that's why for the 3D imaging we are choosing this one, FWI, instead of tomography.
So you need powerful computers, right?
Yes.
Okay. So, what are the problems with FWI?
One you told like cycle skipping, and other I didn't remember, sir.
That's the computational cost, right?
Yes.
Okay, that's good. Anything else? Anybody has any question? You guys need to read more about this and teach yourself, because this is something that you probably get asked to do when you get a job. Okay, it's one of the most important topic nowadays.
Yes,
Okay.
sir. Yes, sir. Anyone who still has any doubt? There's still some time left.
And you can also
Okay,
send
sir.
me email later if you have any question.
Yes, sir. Also, sir, you asked like what is one of the problems in FWI. I think it's very time taking, because if we increase the number of data points, then to compute also we need a lot of, like, it's very contradictory that we need more data points to get a better model, but then also it's time taking to process them, I hope.
Yeah, you're right.
Okay, so a general reminder to all of you that a feedback form link has been shared. So please do fill it before leaving, and the recording of this meeting will be uploaded later on our YouTube channel. Anyone who wishes to ask anything, any doubts? Okay, then it seems there are no questions. Okay, then thank you so much, sir, for being a part of this event and gracing us. And I would like to thank all of the participants also for their patience. And then now it's time to conclude the session.
Okay, thank you. Bye-bye.
Thank you, sir. Bye-bye.